Yeah, what I'm talking about today is joint with it's joint work in progress with Shichi Yu, AHRS Sadeg, and Jesus Sanchez. And maybe what I'll start with, I want to say a tiny bit about the context that our work kind of fits into. This will be this will not be exhaustive at all. So my history is not exhaustive at all. But so there's the original Atiyah Singer. I'm going to run into problems with the board being too low, probably. But, okay, I'll go right away. So there's the original Atiyah Singer theorem. And they also proved a version for families. Maybe I'll go right away to that. So their setting is you have a fiber bundle with compact fibers, and you have a family of, say, elliptic operators on the fibers of that bundle. And they proved a formula for the K-theory class that you get in the base space of the fiber bundle. That was in turn a generalization of the ordinary Atiyah Singer theorem, just on a compact for a single elliptic operator on a compact manifold. Okay, so there's that well-known theorem. There's also an equivariant version of that. So for the case where you have, say, a compact Lie group acting on your manifold, and then people have tried to generalize this in various ways. So again, this is not exhaustive at all, but in terms of the story I'm going to tell, one relevant result is a work of Kahn. So Kahn proved an index theorem for what are called measured foliations. So you try to relax the fiber bundle assumption that you have here, basically. And Kahn was able to do that in the setting of foliations. It's not exactly a strict generalization of this theorem. It's sort of a generalization of a consequence of this theorem, I would say. There's also a stronger theorem that I'm not going to say anything about today, due to Kahn scandalis, which is essentially a direct generalization of this theorem. Okay, but I won't say anything about that today. But this will be relevant for today. And then this was further generalized. So there's an equivariant version of this as well, which is due to, not sure how to say his name, Hitch and Lazarov. And I believe there's other work on. This is the equivariant case. Okay, so if you have also, say, a group acting on your foliation in an appropriate way, there's an index theorem in that setting as well. And yeah, and then maybe closest to what I'm going to talk about today, there's an index theorem due to Flaum, Postuma, and Tang, who generalized a little bit more. So instead of foliations, they consider a Lie groupoid. So maybe I'll say for a measured Lie groupoid. Okay, so in their setting, you look at, say, a family of elliptic operators on the source fibers of a Lie groupoid. So that Kahn was looking at a family of elliptic operators on the leaves of a foliation. You could lift that up to a family of Dirac operators on the source fibers of the holonomy groupoid that integrates the foliation. And so then Flaum, Postuma, Tang looked at this general setting of family of Dirac operators on the source fibers of an arbitrary Lie groupoid. Okay, and actually they did something a little bit more general, which maybe I'll talk about a little bit later. But our project kind of fits in the corner here. This is this is what I'll talk about today. Okay, so we're going to consider a setting where we have a family of Dirac operators on the source fibers of a Lie groupoid, and we also have some additional action on the groupoid. We're also using, I should mention, we're also using very different techniques from Flamm, Postuma, Teng. So they were using some sophisticated algebraic machinery, cyclic cohomology, and so on. We're going to just use the heat kernel method, which is maybe easier for a lot of people, certainly for us. Okay, so that's a little bit about the context. Again, it's a gross oversimplification. There's lots of other projects on various in other directions, but that's maybe roughly how it fits in. There may be two other things I wanted to mention. So in terms of the tools that we use, one of the tools is probably run out of space here. So one of the main tools is there's a theory of Psi-D-O pseudo-differential operators on Lie groupoids. And this goes back to work by Nistor, Weinstein, Shu, and also by Montubert, Pierrot. So they came up with a theory of pseudo-differential operators on Lie groupoids. So that's important. And then, of course, we're also going to use heat kernel methods. So maybe I'll just say local index theory methods. And in particular, the Getzler rescaling method. Okay. Right, and so maybe to kind of start into the mathematics, let me talk a little bit about Lie groupoids. So I think this audience is probably familiar with this for the most part, but maybe I'll at least kind of set up the notation. So I'm going to write my Lie groupoid as G over M. Okay, so there's a range projection and a source projection. I'm going to use R, by the way, just because when you're talking about the heat kernel, I sort of feel T is kind of sacred. It has to be the time variable, so I'm not allowed to use T. Okay, and I'm going to assume that this is a Lie groupoid. I'm going to assume that it's Hausdorff. You might be able to relax this. Probably you can relax this, but I'm going to assume that it's Hausdorff over a compact, in fact, closed. I'll emphasize no boundary. Closed base manifold M. Okay. And right, but maybe I'll emphasize right away that G, the groupoid G, is allowed to be non-compact. So G is allowed to be non-compact. And in fact, in the interesting examples, it's almost always non-compact. For example, the foliation case, G will be non-compact. Okay. So the kind of picture I tend to have in mind for a groupoid is, the groupoid is I have a base space M, and I have these source fibers. So the source projection looks something like that, and you also have the range fibers like this. Okay. G up here. Let's see. In terms of my convention, I'm going to write, for the groupoid multiplication, I'm going to write G1, G2 for the groupoid multiplication. So these are two elements in the groupoid. So this is defined when the source of G1 equals the range of G2. Okay, and Eckart kind of instilled in me that to not get this confused, we should always draw the arrows sort of going from right to left. So if this is I guess G2, G1. Okay, and here I guess would be RG1. Okay, I won't fill that in. right. The Lie algebroid. So Lie groupoid has a Lie algebroid. It's going to be the kernel of the differential of the source map restricted to the unit space. So this is a vector bundle over M. Okay, but it comes with a map. Of course, it comes with an anchor map to Tm. So the diagram like that. And I'll carry this with me. Another piece of structure I'm going to use is a metric. So I want a metric. So h, lowercase h, is going to be a metric on the fibers of A.
So what is the anchor map here? So M is embedded in the
Yeah. Yeah, M is sitting inside G as a unit space. The anchor map would be the range map induced by the range projection. Yeah. So okay, that looks a little bit too much like trace, but I mean the differential of the range projection. Okay. And the metric, right? I want a metric on the fibers of A. Okay, and it doesn't have to have any invariance property, just any smooth metric on the fibers of A. Okay, another thing I should mention is that if you have a section of the Lie algebroid, so if X is a section of A, a smooth section of A, that gives you just like in the Lie group setting. So if your Lie groupoid was a Lie group, then an element of the Lie algebra would give you both a left and a right invariant vector field. So likewise, if you have a section of your Lie algebroid, you get both a left and a right invariant vector field on the groupoid. So these are vector fields on the total space of the Lie groupoid. Okay, and okay, I think that's most of my Lie groupoid notation. Maybe I'll mention the simplest example. So kind of the example to keep in mind, if you like, is where G is the pair groupoid of M. So that's just M times M. Okay. And in this case, the source and the range projections are just the projections onto the two factors. So the range projection is, the range map is projection onto the first factor, and the source projection is projection onto the second factor. And the groupoid multiplication looks like this. So if you have two pairs like this, the way you multiply them in the groupoid, well, okay, so for the groupoid multiplication to be defined, these two points in M have to match, and then the groupoid multiplication just looks like that. They don't have to be proper, no, but they are smooth submersions. Yeah. So G is allowed to be non-compact. RNS don't have to be proper. But I will be assuming that M is compact. Yeah. Right, and in this case, okay. So in this case, right, the Lie algebroid is just a tangent bundle of M, and a metric on the fibers of A is just an ordinary Riemannian metric on the manifold. So H is just an ordinary Riemannian metric on M. Okay. And actually, I meant to put in one more assumption up here. I'm going to assume throughout, that the rank of A is even. Okay. maybe the last thing I should have said here is, what is the unit space in this example? Of course, it's just the diagonal inside M cross M. So the unit space in this example is just the diagonal embedding of M. Yeah, okay, so next let me talk about Dirac operators. So our theorem will be about Dirac operators. So to define a Dirac operator, you need Clifford algebras. So I use the metric on A to build the Clifford algebra. And okay, the metric on A induces one on the dual bundle A star. And so I can talk about this bundle of Clifford algebras. This is a bundle of Clifford algebras over N. Okay, and just to remind you how this works, if you have two elements of A star, say in the fiber of A star over some point, say alpha and beta, and the Clifford algebra is the algebra that you get by, okay, so it's generated by the fiber of A star, and you impose the relation that looks like this. So I'll just write H star for the dual metric on A star, the induced metric on H star, and you take the algebra generated by A star subject to this relation. Right, and then the next ingredient we need to define a Dirac operator is a Clifford module bundle. So E is going to be a bundle of Cliff A star modules. So it's a vector bundle, and each of the fibers is a representation of the corresponding Clifford algebra fiber at that point. And so I have a map. In particular, I have this structure map from the Clifford algebra to endomorphisms of my bundle. And then the next thing we need is a connection on E. So if you're familiar with the ordinary definition of Dirac operators, this should all look very familiar, I would say. We're basically just replacing the cotangent bundle by A star everywhere. That's all we're doing. So we need a connection. So nabla is going to be connection on E. Oh, sorry, misspoke slightly. Okay, it's not an ordinary connection. It's going to be what's called an A connection. Okay, so if you take the definition of an ordinary connection, and everywhere where a vector field appears, you replace it with a Lie algebroid. Yeah, Lie algebroids are sort of by design, they behave very much like the tangent bundle. So everywhere where a vector appears, you replace it with an element of the Lie algebroid. That gives you the definition of an A connection. I'm going to assume that my vector bundle E is equipped with an A connection with the property that so it's going to have a compatibility property with this Clifford action. So the property I want is that if you take a commutator that looks like this, so here X is an element. Sorry, X is a section of A, and alpha is going to be a section of A star. I want this to equal, so these are both operators on sections of E, so I can take their commutator, and I want this to equal this operator. And what this is here is what you might call the A Loizides connection. So you take the definition of the Loizides connection, and again, wherever a vector appears, you replace it with an element of the algebroid. That gives you something that you might call the A Loizides connection, and that's what's appearing here. So this is the A Loizides connection. Okay. Okay, so I want to assume that the connection has this property. Again, this is the standard thing you do when defining a Dirac operator. I've just replaced the tangent bundle with A everywhere. Okay, so once you have this structure, we can define a Dirac operator. So then Dirac operator, or maybe I'll call it the A Dirac operator. And besides, it's not quite the ordinary notion of Dirac operator. So the A Dirac operator associated to this data, so E, its Clifford action, and this connection is so it's going to be given by the usual composition. You apply the connection and then use the Clifford multiplication. So you start with a section of E, you apply the connection to it, the A connection to it, that lands in sections of A star tensor E. Okay, so again, for an ordinary connection, T star M would appear here, but now I've got an A connection, so of course A star appears here. And then you apply the Clifford multiplication. Okay, and this composition is the Dirac operator. This has a lot in common with the ordinary notion of a Dirac operator. So for example, if you square it, if you look at d squared, which I'll call delta, this is a kind of A Laplacian operator. Okay, so this is what deserves to be called an A Laplace type operator. It obeys a kind of Bochner-Licknerowitz formula. Again, you just replace tangent bundle with A everywhere, basically. Yeah, but I should emphasize that one thing that's very different is that often this is not an elliptic operator anymore. So the Dirac operator is famously an elliptic operator. You square it, you get the Laplacian, which is a nice elliptic operator. These operators are often not going to be elliptic anymore. So for an example, if you take the foliation case, if you look at the foliation case, I guess I haven't written that on the board yet. Maybe now is a good time. So the remark is that D need not be elliptic. So for example, if you take, if F is a foliation of M, and you take the Lie algebroid to be the tangent bundle to the leaves of the foliation. Okay, so this is a Lie algebroid. Then what this D will end up looking like is just a family of Dirac operators on the leaves of the foliation. Yeah, so D will basically be family of Dirac operators on the leaves. Okay. So in particular, typically it's very far from being elliptic. It's only differentiating along the leaf directions. Even in the B tangent bundle, it won't be case. It won't be. It's not. It's not. I'm not even sure it's true if A is transitive because I think you could have cancellations. Yeah, you could have too many terms and they cancel out maybe. So I'm not 100% sure.
Is there a sense
Yeah.
of which is partially elliptic or elliptic in some direction? Or?
I mean, I think of it a little bit informally, maybe not quite correctly, as differentiating along the orbits of the Lie groupoid action. Well, okay, maybe there's a better answer to that question. So there's another perspective. Was I going to say this next or in 1 minute? I was going to say this next anyway. Okay, so there's another way to think about this, which you might find simpler. We can go back to this picture I had of the Lie groupoid. So we have G over M. And maybe I won't bother drawing the range fibers this time, just the source fibers. Okay, so we have the source projection, and what I'm drawing here are the source fibers, the fibers of the source map. Okay. What you can do is you can take all of this data that I've been talking about, the metric on A, this bundle of Cliff A star modules, and the connection. You can pull all of that back under the range map. Yeah, so pull H, this bundle, and the connection back under the range map, and then what happens? You see, if you take the pullback of A, this bundle A under the range map, what you get is well, it's canonically identified with the kernel of the source projection. So with the vertical bundle for this projection. Okay. And so what that means is that this metric on A or A star becomes a metric on the vertical bundle of this submersion. And likewise, this becomes a family of Clifford modules on the fibers of that submersion. The connection becomes a family of connections on the fibers of that submersion. And the Dirac operator becomes a family of Dirac operators on the source fibers, on the fibers of that submersion. So maybe I'll just write down the Dirac operator statement. So D, well, okay, I'll write down, say, the metric. So R star H becomes a family of ordinary Riemannian metrics on the source fibers. Oh, and it's not just any family, it's a G equivariant family. Comes a G equivariant family of ordinary Riemannian metrics on the source fibers. Okay, and likewise, the Dirac operator. Okay, so the Dirac operator induces a right invariant. So maybe I'll write dr, kind of consistent with my notation for right invariant vector field. So you get a G equivariant right invariant family of Dirac operators, of ordinary Dirac operators on the source fibers. Okay, so there's this other perspective. There's this family's perspective where you think of your A Dirac operator as a G equivariant family of ordinary Dirac operators on the source fibers of the Lie groupoid. Okay, and from that perspective, that perspective is closer to the Atiyah-Singer family's index theorem, right? So Atiyah-Singer are looking at the case where not only do you have a surjective submersion here, but you actually have a nice fiber bundle with compact fibers. So in a sense, the way we're generalizing is that now we're allowing something that's maybe not fiber bundle, it's just a surjective submersion. The fibers don't have to be compact. Yeah, I see. Okay, I see multiple questions. Yeah.
No, just because, but then in the direct case, everything we use with single fiber, we
Yes. Yeah. Well, these operators you get on the fibers are definitely elliptic. Yeah, but the induced operator on the base, I'm not sure. Yeah, okay. I need to think about it. Yeah, I saw Dan, you had a question? Yeah, exactly. Yeah. So actually, when I wrote up that kind of one history blackboard, I should have written, this is sort of very incomplete history of longitudinal index theory. Yeah, we're doing index theory on the source fibers. Yeah. So there's also transverse index theory. I'm not saying anything about that today. Yeah. Probably, yeah. Naively, I would guess that the transverse theory might have a better chance of being well behaved under Morita. Yeah.
Can you look up a symbol that lives on A star as opposed to T star?
Yeah, definitely. Yeah, yeah, this operator you can definitely assign a symbol that lives on A star, and it's the usual thing. Basically, it's a symbol, an ordinary Dirac operator. Its symbol is Clifford multiplication, and that's also true here. Okay. Okay. Maybe I need to go a bit faster. Okay, so let me say a tiny bit about the convolution algebra. So the groupoid has a convolution algebra. And I think the nicest way to do it is with densities or half densities. So I'm going to write lambda for this bundle, and maybe I'll complexify. It's not a big deal. Okay, so these are, this is the bundle that when you pull back under the range projection, like what I was doing over there, become densities on the source fibers. And then there's this algebra, which I'm going to call psi minus infinity g. So this notation is motivated by the fact that when you start thinking about this pseudo differential calculus that I mentioned at the beginning, these will be the smoothing operators in that story. Okay, so this is the smooth compactly supported sections of r star lambda to the half tensor s star lambda to the half. So I'm just sticking in some half densities in order to make the formula for the convolution as nice as possible. So now the convolution, so this thing is an algebra and it has a convolution product. So if you have two sections of that form, involve them like this. Okay, here I use 0 for some reason in my notes. So you just integrate over the set of arrows satisfying G1, G0 equals G. And then you do F of G1, F1 of G1, F0 of G0. Okay, and because of the densities, you don't need any measure. This just makes sense. Which goes from where to where?
So the convolution product goes from where to F0 and F1?
They live in here. So I'm saying that this is an algebra with this product. Yeah, so if you have two sections of this bundle, I should have maybe emphasized this is a bundle over G. It's a bundle over G because I pulled these things back. So this is some line bundle over G.
That needs to be a density on.
Yeah, it takes maybe a couple minutes of staring at it to check that all the densities work out, and it's really exactly the thing you need in order to be able to integrate over this set. But it does work. You can also do this by just introducing a family of measures, what people call a yeah. Okay, and maybe I won't get into this. I don't think it's so important for this talk, but as I mentioned, this corresponds to the smoothing operators. So if you set up the whole pseudo-differential calculus, this corresponds to the smoothing operators. So there's also much, there's also a larger thing which you might call psi infinity of G, an algebra of pseudo-differential operators on the source fibers of the Lie groupoid, and this thing sits inside here as an ideal. Okay, but I don't think we'll really need that today. Okay. Next thing I should say a little bit about is what is a trace. So a trace on an algebra A is just a linear map, say tau from A to complex numbers, with the property that tau of AB is tau of BA. So that's what I mean by a trace. And we're only going to consider, so I'm going to consider traces on this algebra over here. And we're only going to consider traces of a certain form. So we only consider traces on psi minus infinity G that factor as follows. So if you have something in psi minus infinity G, you can restrict it to the unit space. And when you do that, you get a section of this bundle lambda over M. And then you can apply a continuous linear functional to this. So continuous linear functional. Okay. So I only want to consider traces that have a factorization like this.
Lambda is a bundle over M.
Yeah. Yeah, so this is something that lives over G. Yeah, you restrict to M, and then those the two 1/2s combine and give you a lambda, and you end up with a section of lambda. And then I want to consider only traces that have a factorization of this form. You could probably look at more general things, but this will be enough. So they're completely determined by this piece, and this piece will be determined by a section, a generalized section. So by generalized, I mean it could be a distribution of so lambda inverse tensor with something that I'll call lambda m, and lambda m is the ordinary density bundle on M. Because if you have some section of this bundle, you can combine the lambda with the lambda inverse to get rid of the lambdas, and then you end up with a density on M, which you can then integrate over M. Okay. So a continuous linear functional is going to be they're in one-to-one correspondence with generalized sections of this bundle. Okay. No. So I was going to say that next. So the condition of being a trace imposes a very strong condition on this section. so one of the nice things about this bundle is that there's a canonical action of the groupoid on this bundle. I don't think I have time to explain that, but there's a canonical. So this bundle appears in different contexts. For example, when people talk about modular characters in Poisson geometry, and also volumes on differentiable stacks, this bundle appears. So there's a canonical G action on this line bundle, and the trace property is equivalent to this section being invariant. So it should be a maybe I'll put a prime here for a generalized section. So lambda inverse tensor lambda m should be G invariant. Okay, and I should mention an example. Okay, I'm low on time. So going back to this example where G is the pair groupoid, M cross M. So in this setting, there's only one possible trace up to scale. And that trace is just integration over the diagonal. So this is the diagonal. Okay. So in that setting, lambda inverse, lambda and lambda m are the same. So this is just a trivial bundle. This corresponds to the constant section 1 of that trivial bundle. Okay. But as a functional, on the on psi minus infinity G, it's just integration of a density along the diagonal in M cross M. Okay, so it's the ordinary, if you like, it's the ordinary trace on smoothing operators. It's the ordinary trace on smoothing operators. Okay. Okay. Okay, I think I'm running out of time a little bit, so I'll have to jump over some things. But okay, so I'll state some things as facts, which might be familiar to some people, but I'll state them as facts. So why we care about traces is that a trace induces a group homomorphism from the K theory of an algebra. So in this case, psi minus infinity G. To say the complex numbers. Okay, and if you think about this group, say in terms of idempotence, you basically just apply the trace to the idempotent. That's all this map is. Okay, so this will be the sense in which our theorem is topological, quote unquote, in the end. Okay, the other thing which I'll just state as a fact is that this family of Dirac operators that we have on the source fibers. So maybe I'll call that this A Dirac operator. A Dirac operator determines a class in K theory. Which I'll call ind D. You might think of it as the index class. Determines a class in the K theory of this algebra. And so you can ask about, so what we compute in our theorem is the action of this trace on this index class. That's what we compute in the end. And in the pair groupoid case, which I just talked about, this boils down to the ordinary index. So this index class is just basically the analytic index of your operator in the sense of a T.S. Singer. And when you apply this trace to that class, you would just end up with the difference of the dimension of the kernel minus the dimension of the co-kernel. Okay, I'm sorry that I'm rushing. Going to run out of time, but let me say very briefly what I mean by a group action, and then I'll state the main result, and then that'll be a good stopping place. Okay, so there are different things you might mean by a group action on a groupoid. So I'll say what I mean here. So gamma, I'm going to write gamma for just an auxiliary, a compact Lie group. Okay. The kind of action I want to consider is what I'm going to call an action of gamma on G by bisections. I'm open to suggestions if someone has a better idea what this should be called, but an action of gamma on G by bisections is a group homomorphism from gamma to the group of bisections of G. Okay. Bisections of G, these are submanifolds of G, such that when you restrict either the range or the source map to that submanifold, it becomes a diffeomorphism onto the base. Okay. And that forms a group under multiplication, usually some infinite dimensional group. For example, in the case of the pair groupoid, this is a diffeomorphism group of M. Okay, so I want a group homomorphism into the group of bisections of G, and it should be smooth in the appropriate sense. And okay, so that's what I mean by a group action. And I think now I was going to talk a little bit about properties of this, but I think I'll skip over that. There's an equivariant version of this that you can study, where you can twist this by a group element of gamma and get a more refined quantity. So this is just a complex number. But when you have a group action around, just like in the ordinary setting, there's a way to twist this construction in order to get not just a complex number, but a function on the group. So there's a notion of equivariant index, and that's really what we compute. So now I'll just write down the main result, and then I think I'll be out of time. So our main result is a formula for that quantity. Okay, so maybe I won't write down all the assumptions again. They're the assumptions that I've been kind of carrying along all the time. So it's a formula for. It's the following formula. So we have a formula for the pairing of some trace with the index class. And as I said, in this equivariant world, there's a way to twist by some element of the group. So I'm going to stick in an element of the group. So gamma is just some element of this group. And so the answer is some complex number, and the formula looks like this. So it's a certain pairing. Yeah. Okay, I'll talk about this in a second. I have the what you might call the fixed point subset of M under this element gamma. It embeds inside the unit space M. So this embedding is going to appear in the formula. So you pull back tau to the fixed point set. You have to divide by something, and then you have some characteristic classes. We're using notation for the characteristic classes, basically as in Berlin Getzler Verne, except that and all this, you should take the top part. Okay, so so in the example of the pair groupoid, let me say what this is, and then I'll explain what happens in the general case. Oh, I'm already out of time. Okay, let me skip that then. Okay, so this is very much like the ordinary fixed point formula for the index in the pair groupoid case. It is exactly that in the pair groupoid case. In general, the differences here are, so these characteristic classes that appear here, they're what you might call A characteristic classes. So you do Chern-Weil theory with A connections instead of ordinary connections. You use the ordinary formulas for Chern character and A roof genus, and that's how you define these things. This pullback of J divided by nu. Okay, basically, think of the pair groupoid case. Tau represents integration over M. When you pull this back to the fixed point set, that becomes integration over the fixed point set, essentially. And here we're dividing out by a density in the normal bundle direction determined by the metric, basically. Okay, and I should stop there.